And over to you, Marcin.
Do you hear me? Okay. My name is Marcin Krotkiewski, and I work at USIT, which is a supercomputing department at University of Oslo. And I will show you today the work I have done within an advanced user support project. This is a service NVIS has for the users that need some advanced help to adapt or improve their codes to run on supercomputing infrastructure. And this particular project was about optimization and parallelization of NORWECOM code for shared memory architecture. So no MPI this time. This was just OpenMP. So some words about the code. It was a sequential code in the beginning, a three-dimensional code developed in the 80s and 90s. It was a mixture of Fortran 77 and Fortran 90, which means that there was dynamic memory allocation capabilities already used in that program, which is actually quite important for this particular project. And the program mostly dealt with advection and diffusion of nutrients and contaminants in seawater to model the fish populations. It was a special code in the sense that although it was three-dimensional, you had something which would be called terrain maps, which would be essentially 2D, and then you would have a third dimension, which would be the depth component. And the maps would tell you where in your model you had water cells and where you had land cells. And calculations would be done only for the water cells and not for the land cells. So the map would essentially decide where you do calculations and where you don't have to do calculations, which was a one of the tricky parts to improve that code. So when we want to optimize or adapt the user's code for the modern architectures, we actually have to understand first how such architectures work. And you have heard quite a lot about this today earlier, I think. Let's briefly reiterate. So each compute node of Betsy, which is our largest supercomputer, has 128 CPU cores, which can all use the 256 gigabytes of RAM that is on every compute node. And then the question is, okay, you have 128, let's say, CPUs, and they can access the same memory. So each single CPU can allocate all of it if it wants to, but how do they practically, work together on that memory? That's quite important. So if you look at how this CPU architecture looks from inside, it's actually built from modules, let's say small blocks. You see that the CPU cores are arranged into groups of 4. They share something which is called L3 cache, so they share some small piece of memory together. Then, together with another such block, they are arranged into what would be called a die. And then those dies are then arranged into a bigger, let's say, CPU. You see here the dies between each other, they talk, they have to exchange data. They exchange it using what's called infinity fabric on AMD CPUs. And each of the dies has some memory connected to it. And that's quite important because if you look at the die 1, it can access memory on the die 3, but it will take longer time because, the CPUs will actually have to go through this infinity fabric, talk to this guy and ask him to get this memory. This is what you heard today earlier. This is so-called Numa or non-uniform memory access machines. Accessing different areas of memory takes different amount of time. So from this perspective, those CPUs really look like small clusters that actually have interconnects inside them. You just don't see it from the perspective of a user. So optimizing of this particular code for shared memory machines involve first and foremost memory-related code changes. So we had to make sure that the memory is accessed linearly. I will show you what that means. Then we wanted to make sure that the compiler can vectorize the code. When that was done, the code would be parallelized using OpenMP pragmas. That required some care and attention when it comes to memory allocation and initialization. And then in the end, we did some performance analysis on the result to see, okay, is this code already good, or can we improve it better? Even more, is it worth it, or are we actually satisfied with the result? Okay, so first of all, this was a 3D code, as I said. So in Fortran, you would, let's say, look at it as a 3-dimensional array. But how is that actually stored in computer's memory? Computer's memory is linear, it's not 3-dimensional. So we have to arrange the data inside of the memory somehow. And in Fortran, the 3-dimensional arrays are stored in column major order, so-called. So let's assume we start here, and then we put byte by byte or value by value in the memory. We put the whole column, and then we put the next column. So we go to the next column, and after the first one, there comes the second one. It's actually quite important, because then later when you compute on those arrays, when you use them in the calculations, you really have to make sure that you know how this data is arranged in the memory. So on the left, you see what was there before in the original code, and you see that the innermost index, which is iterating over the column, so along these arrows, here, it was actually the second index from the top in this loop next, and the innermost index was the K index. So it would, instead of going along the arrows, instead of actually computing first for this value and then this value, it would go orthogonal somewhere there, for example. And this is very bad for code performance on modern machines. So we should always make sure, and this is a universal truth for this type of codes, it's always like that. You should always make sure that this innermost or fastest changing loop index is the innermost loop. So this is one of the things that we had to change in all of that code, because it was written for a different architecture and it was optimized for different kind of rules. So that has to be changed. Then when you look at the modern CPUs, what you see is they can actually compute on vectors of values. So instead of doing calculations on one set of numbers, 1 + 2 = 3, they do all of that in one go. Okay, so for AVX extension, they can do 4 doubles in one instruction. But you also have to make sure that you arrange the calculations correctly for the compiler to see this. And again, as before, it's important to do this so that this fastest changing index is the innermost index. And it's nice because it's consistent. You always have kind of this rule applies also here. So this loop on the left would not be vectorized because the compiler would not see that he can actually work on small vectors here, because we jump along the K vector. So he doesn't see those vectors because they're here. And this loop would get vectorized because the fastest changing index is the innermost in the loop. So this is nice. The compilers are actually quite smart at doing that, and you can use it in almost any compiler now. This is an example what options you would use for the Fortran, for the Intel compiler. This is for the GNU compiler. It's important when you do that to use those reporting options. This is the last part here, and then that you should also look at the report. So it's not enough sometimes to just make a correct loop structure. There is other data dependencies and other things that stop the compiler from correctly understanding the code. So then if you look at this report, you will see, okay, there is a problem. The loop was not vectorized because of whatever vector dependence the compiler found. And then you have to go in and restructure the loop make some changes, for example, the loop structure itself, but also maybe introduce some temporary variables, temporary arrays, remove the data dependencies if you can, and then if you see something like that, loop was vectorized, then you're happy. Then that means that the code has been vectorized by the compiler correctly. After that has been done, then we went on. So first I started with, let's say, the sequential code. So here we don't talk about parallel execution yet. Everything that was done up to this point was executed and optimized for a single core. And then you go on to parallelize the code. In this case, it was just parallelized using OpenMP. So again, from the compiler point of view, it's really simple. You just have to add this flag, and then you have to place the OMP directives somewhere in the code. So in this case, we just have this loop, and we put the directives around it, and we add this OpenMP compiler option, and it's done. So more or less, that was it. The code has been parallelized. The question is, of course, is it efficient now? Because now we go back to this first figure. How do we make sure that whatever thread, whatever the CPU located in this die, whatever the thread running on that CPU is doing, how do we make sure that it's actually using this memory and not that memory? Because if it's using that memory from die 3, it will be slow. It will actually be much slower sometimes than when you just run sequential code. That can actually mess things up quite a lot. So one of the things that is done to make sure that this is actually done like this is you have to allocate the 3D arrays in a special way. So Fortran allocation of data in Fortran looks like this. You have this allocate directive, and it doesn't say anything about where the data is located, on which CPU or in which memory DIMMs, in which hardware. It doesn't say anything about this. But it also doesn't allocate anything yet, really. It just makes a logical array that has this size. What you have to do then is you have to use the so-called first touch technique. And then you make an initialization loop, which should be structured exactly like your compute loop. So it should have the same OMP, pragmas, it should have the same loop order. And then you should walk this array that you allocated in the same way and then initialize it. So you actually first touch it, you write data to it. And what happens then is the Linux kernel actually makes sure that the data each thread touched is located close to that thread. So this is enough to, this is usually enough to make sure that actually then later, in the end, whatever you compute on is located in the correct memory banks. That is a nice trick, and actually most codes would use this technique. Okay, so this is more or less the extent, roughly the extent of what we were doing in that particular code. Then looking at the performance, you have different tools. I saw Radovan would show you some results. I don't know which tool that was. I was using Vtune for this project. On AMD, you can also use, on AMD architecture, you can use Code Analyst. And then you run instrumented code, or you analyze the CPU counters, performance counters through that application, and then you get a report. And as speakers before me said, you look at, for example, the floating point performance or floating point utilization of this code, and you see, wow, it's terribly slow. I'm using only 2.3% of the CPU capabilities, so it's horrible. It's actually very bad performance. But in fact, what happens is this code mostly moves data around. So when you read the data, when you access the arrays, if you look at the loop here, so there is no calculations done here. The FPU or the CPU floating point units, they don't do any work, but there is a lot of work done by reading and writing the data to the memory. So then if you look at the memory report, you will see, oh, that's 52% of my memory bandwidth. That's actually not too bad. And in practice, you should not expect more than this. It's only synthetic benchmarks that can get up to 70, 80%. What you get with user application is never above this threshold is actually quite good. So then you can say, okay, that code has been optimized. I don't need to do much more. You can also look with the Vtune, also with code analysis. I guess you can look at hotspot analysis, so you can see which routines, which modules take most of the time in your calculations, and concentrate. If you really want to improve something, concentrate on those, because here it makes sense to improve anything in the first three, but it doesn't make sense to spend time trying to fix that last routine, because it's in the whole scheme of things, it doesn't take so much time. So such tools will give you a good overview of what you should concentrate on when you optimize your codes. Okay, so as a summary, what we were doing in this particular project, enabling compiler vectorization. So again, changing the code a little bit to make sure that the compiler can do the work for us, to vectorize the code. And that would involve re-implementing of some modules, restructuring some of the loops, adapting the code to be Numa aware. This is by far the most important thing that has to be done on modern shared memory architectures. Without doing this, without making sure that the code actually understands and behaves Numa friendly, the code will never scale. So we have to do this. Then when that's done, you can do OpenMP parallelization. We analyze then the performance to check, okay, we are happy with the performance. There's not much left that we can do because we are 50% efficient. So, more effort would not bring so much improvement. And then in the end, it turned out the code was 2 times faster sequentially, so not that much, but then around 20 times faster when executed in parallel on one compute node of Fram. So that was the outcome of this project. Okay. I hope you heard me.
Yeah, thank you. Thank you, Marcin. I see there is not the questions on HackMD was answered. Is there any?
Yeah, Dani, I would like to ask a question from Marcin.
Yeah.
So, Marcin, when you vectorize this code, we don't know the values of these variables, whether they will fit on the memory we have without going through the InfiniFabric, for example. How do you know, like without knowing the values of these variables, what values they would have, to see whether that will fit in the memory?
How do I know the values of which variables?
Let's say if you want to do the calculation on one die, it has access to a limited amount of memory. So how would you know, without knowing the values of the variables, that whether it will fit?
Whether they fit?
Yes.
Well, I mean, I think Ule was showing before a tool which is called Numa CTL. If you, I could maybe I can show you if I can switch to a different window. I'm not sure this answers your question, but maybe it does.
Yeah, I'm trying to connect Ule and you and some concepts discussed.
Yeah, I am here, but what Marcin say about the Numa control is a very good way of doing it. Using Numa control.
So I think this is the Betsy computer, and then let's say we go to one compute node, and I don't think you guys can do it, but I can do it because I can just SSH there, and then if I type Numa CTL -H, then I will get this Numa information, and then you see that, okay, node 0 has this and that amount of memory. It says 32 gigabytes, right? And so this will tell you what the architecture is, and this will tell you how much memory can allocate on each such node. So as long as you're below that, then you should be good. Of course, in some cases, it's actually important that you access the entire memory for some databases or something. So then you don't care so much what the penalty is. You run a sequential database and you allocate in all of them. But for supercomputing applications, for what most of us are doing, is actually important that we share the work, or we split the work between the threads, but we also split the memory between the threads. This is very important to make sure that the code is scalable. Otherwise, it won't scale. It simply will not scale. Does that answer your question, Sabri?
Yes, thank you, Marcin. Thank you.
Thank you, Marcin. Is there any more questions to Marcin?